Welcome back, everyone, to the second session of the Virtual Flow Forum. In this session, in the last session, we heard Kathy Borer talking about data quality and its importance, and we also ended the last session talking about managing data. I know it's a massive issue in the water industry. We've got an absolute flood of data coming towards us, and managing data is going to be more and more important. So this whole session is going to be a discussion with George Heywood of Ovarro, Ronnie Bains of Seeq, and Darren Steele, as well as Sam Greene of Southern Water. And we're going to talk about the challenges that the water companies are going to have in managing data, the value of that data, and how, with the solutions that are on the market right now, we can manage the data to get that insight that we need that will help with pollutions, that will help with flow management through the wastewater system. So at that, I'm going to introduce our first speaker for this session, who's George Heywood of Ovarro. George has had a very, very long experience within the water industry. I know George did quite a lot of the work on DWF and the Q80 work. As well as I work with George on the UpWeir project on FFT. And George's going to talk about a rough guide to flow data validation. So if you want to take it away, George.
Great, thanks Oliver, thanks for having me in the presentation today. It's really good, and morning everyone. So Ovarro, you probably know, is a company that provides monitoring and control software and hardware for the water industry and other industries, and we also do quite a lot of analytics based on those data to give extra value to them. And as Oliver's been saying, one of the areas that I've been particularly involved in over the years is analytics on wastewater flow data and also EDM data. So we're going to start off this session with some quite a kind of technical presentation. No apologies for that. I hope you enjoy it, about flow data validation. So I press my clicker. So what does validation mean? It's the act of checking or proving the validity or accuracy of something, according to the dictionary. So why do we need to validate flow data? And a few reasons here. So first of all, we need it because we do need to do that because so that we can exclude invalid data from an important calculation. And we've been hearing a lot already this morning about compliance assessment, and that's probably the most important calculation. But also planning and design calculations, we need to make sure that those are not being polluted by invalid data. And then secondly, so that we can fix a problem with the measurement, we can find out that something is wrong, and we can go out there and fix it so that we can collect better data in the future. And then thirdly, so that we can react quickly to an event of concern. So there might be something real going on that is causing this unusual data that we're seeing, and we want to be able to react to that. And that's probably what we would call anomaly detection. So it's not so much validation, but there is a kind of grey area between validating data and identifying something real that is going on, that is unusual. So what kind of things can go wrong with flow data? So first of all, there can be a problem with the measurement structure, an obstruction in the weir maybe. The sensor might be pointing in the wrong direction, leading to constant values in the data. The monitor might be set up incorrectly with incorrect range settings, and that can lead to truncated high values or indeed truncated low values, and it can also lead to discretisation in the data, and we'll look at that in a few minutes. There can be changes in calibration for better or for worse that can lead to a kind of step change in the data that we're observing. There can be a loss of power or communications, or finally there could be a real world problem, a real world event nothing to do with the monitoring, but to do with the process or the flows arriving, and we need to know about that as well. So the flow data is an example of time series data. It's a number of data points collected over time at a regular interval. And there's a number of different types of validation that you can do on these kind of data. And I'm going to look at each one of these just now and with some examples. So first of all, obviously, there can be missing values, nothing arriving at all in the signal. Secondly, there can be outliers, unusually high or low values that we need to identify. So sometimes there can be near constant values, so not exactly constant, but quite close to being constant, perhaps, and this could be the sensor pointing in the wrong direction, maybe, or pointing at an obstruction. There's that discretization that I've mentioned, and then step changes in calibration, and then finally the summary data that we're deriving from the time series data. These might be the daily values being derived from the 15-minute values. We need to identify invalid data in those data as well. So okay, let's start with the outliers one, and there's a number of ways that we can identify outliers in time series data, and we'll start off with the most simple and then work on to something a bit more sophisticated. So obviously we could have constant thresholds, high and low thresholds, and whenever a number is above those thresholds or below, then we invalidate that data point. But the problem with that is that they need to be set up individually for each monitor, and they might not. The appropriate thresholds that we would want to set might change over time, and so we have to keep on maintaining the thresholds, and that's quite a workload. So a step up from that is to have self-calibrating or adaptive thresholds that respond to changes in the signal in an appropriate way. And and here's an example of one of those that we've used with 15-minute flow data. So we would invalidate 15-minute flows that are less than 60% of the second percentile of the valid 15-minute flows. So we're using a percentile value at the bottom of the distribution, and we're saying if you're lower than 60% of that value, then you're too low, and that's very unlikely to be a real flow data point. And then finally, we can have some kind of smart thresholds that not only adapt slowly over time, but are able to see what is normal within the daily changes in flow data that you might expect. So, and here's an example of that on the right-hand side there. So the yellow points are the data, and then the blue dotted lines could be smart thresholds that could be applied. And there's a number of different ways of generating these. You can the first two there are univariate and multivariate time series forecasting methods. So the difference between those is that the univariate methods only use the flow data themselves, and these are good at spotting things that are out of the ordinary in the dry weather diurnal profile, but they won't be able to respond to a rainfall event occurring. But then the multivariate methods, these can use a rainfall signal as well, and they can allow the upper boundary there to flex upwards in the event of a rainfall event. And then perhaps the most sophisticated on the list there, the third one, is machine learning approaches such as artificial neural networks. And quite a few companies are beginning to apply these to identify anomalies in wastewater flow and level data, and it's an approach that can be used for validation as well. So, okay, so that was outliers. What about near constant values? So an example there of that on the right-hand side, we've got some normal dry weather diurnal changes on the left, and then there's a rainfall event, and then at the end of that event, something goes wrong, and we see this kind of flat area of near constant flow values, and that's not valid data. The way that we usually detect this is by calculating the coefficient of variation on a rolling basis, and that's the standard deviation divided by the mean. Sorry. There we go. So my clicker is being a little bit slow to respond. That's it. So, for example, where there are 5 consecutive data points that have got a coefficient of variation of less than 0.003, we tend to use 2 different methods in parallel here. So we use that one, and then we also look for 20 consecutive data points with a coefficient of variation of less than 0.015. These are, you might want to choose your own values here, but these are ones that we found to work well for wastewater treatment flow data. So do go ahead and copy them if you want to. Now, obviously, the thing you've got to watch out for here is that there might be near constant flows because of the effect of the storm overflow weir during a long rainfall event. So we need to make sure that we're not invalidating those flows at that weir level. So we use this third bullet here so anything that is greater than 95% of the 95th percentile of the valid flows, we do not invalidate those data under the above rule. Okay, so discretisation I mentioned, and on the right there's an example of what you might see if the data are suffering discretisation. So for this graph, I've put some blue dots on the data points just so it's a bit easier to see. And you can see that we're not getting a full continuous range of flows being recorded. Only certain numbers it's like the monitor can only record certain values. And in this case, there are only 10 different values being recorded. And this can be caused by incorrect range settings on the monitor, or perhaps incorrectly sized monitoring equipment. And what we would do here is to invalidate data where there are fewer unique values than would normally be expected. So, for example, we might invalidate days on which the number of distinct flow values is less than 20. Ideally, you'd want more than 50 distinct values to be sure that you're getting a reasonable precision in the flow monitoring. Okay, and the next one here, validating step changes in calibration. So if there's been a change in calibration of the monitor, and that's leading to a step change in the flows that are being recorded, then either the period before the step change or the period after is likely to be wrong, and hopefully it's the period before the step change. So we can do that by again applying one of these time series models. I'll just show you an example of that. So here's some flow data, and you can see that the diurnal profiles to the left are a little bit lower than those to the right on the graph there. And so what we do is we create a time series model that is trying to reproduce these data, and that's the black line on the graph. And you can see it's fitting quite well to the left-hand side, but then you begin to get a divergence after the change in calibration. And so when we calculate the error between the real data and that model, and that's the red line on the chart there, and it's plotted against the right-hand axis. And you can see that the error is centered quite tightly around the zero line, horizontal line there on the left-hand side, but on the right-hand side it goes up to show a systematic positive error. And if we just put a couple of, that comes out more clearly there if we apply these horizontal lines in red. And what you can do is you can use a technique like QSUM to identify the step change and then use that perhaps to invalidate the data prior to the step change. And then finally, invalid summary data. So far I've been talking about the validation of the 15-minute data, but often we're wanting to calculate daily summary values. Certainly we would be doing that for calculating dry weather flow. So what should we do when we're calculating these daily values? What should we do about the invalid 15-minute values? So what we tend to do here is to set a threshold whereby we would invalidate daily values that have got fewer than a certain number of valid 15-minute values. And a number we've tended to apply here is 92. So if you've got 92 out of 96 valid 15-minute values, then you can calculate a valid daily value. And then we would often also go back and invalidate all of the 15-minute flows on those invalid days. So having done the validation, sometimes we find that you would need to fill in gaps in the data where data have had to be removed because they were invalid. There are occasions when we do need a complete data series. And there's a number of approaches for doing this. So if you just got a very short gap, maybe just 2 or 3 15-minute values, then you could do that with just applying a linear interpolation, kind of joining the dots in a straight line to infer values in the gap. If you've got a larger gap in dry weather, then a time series modeling approach like ARIMA, again, you could use to fill in data in that gap. And if it's in wet weather, then you might need to go to something more sophisticated that can model those changes that are being driven by the rainfall. And in all of these, you might need to truncate the result to reflect the effect of the storm we are setting, because the models may not adequately do that. Okay, so just in summary, this is what we've looked at. We've gone through a few different approaches for validating flow data, and I hope that's been useful. I think I guess it's something that a lot of you have had to think about in the past, and be interesting to hear your thoughts in the discussion. Oliver.
I must admit, the vast majority of those I've come up against. The best one is certainly with the level-based open channel flow, where somebody's just put a metal plate underneath the sensor, and you get a completely flat line, and you're suddenly going, so what's going on here? I've had discussions recently where you've got the data within the instrument. So people are starting to talk about using the HARP protocols that are already in the instrument, and using those also to help with the data quality. The decision I've had to have in the past is I'm sat at a computer in the office, I've got a flow meter 60, 70 miles away, or 2 hours away in the car or whatever, and you're suddenly going there, so what's the problem here? But as we heard from Kathy, it's only the data quality is only going to become a massive problem, as well as everything else in the future. So it is really good. But we have got a question from Andrew Chappell. the agency, how do you set the initial percentile thresholds?
So you mean that those numbers in those kind of percentile definitions that I was putting on the slides? I think we've built those up through experience over quite a few projects working with flow data. I think we found those to work quite well as a kind of rule of thumb. I think it's probably something you want to keep under review and make sure you're looking at the reviewing from time to time the values that are being invalidated by the rules, checking that they're still appropriate.
I must admit, when I was at Anglian, we had a system which was upper and lower boundaries. So, and the upper, if a total daily volume was in or outside the upper lower boundary, then it would flag after 3 days, and that worked. It was rudimentary, but it worked. But certainly, it wouldn't necessarily cover some of the case studies that you had there. So where you,
I guess you had to set them up into.
Yeah,
you
did.
To set them up individually for each site.
You did, yeah. We had a general rule of thumb, but as over the years that we found sites that were okay, then we could tighten those boundaries, tighten until we got to a break point, and that allowed the sensitivity to change, but not getting false alarms all the time. So, and that was the challenge. But to be honest, I don't envy the people that were in my situation at Anglian now, because they've got a lot more coming to hit their plate with EDMs, with UMON 4s, with final effluent, with UMON 3s. And it's going to be a case of bringing all that data together. That there's going to be a real challenge for the industry. So data quality moving forward is going to be, well, when we're talking, I mean, I said earlier, a rough figure of 500 million pieces of flow data every year. And that's 15-minute values. And that's if the data is pretty much perfect. What you'll find, what I found in the past, is you've got telemetry repeats. So it should be a neat every 15 minutes, but then you'll suddenly get a spurious data point from 11 minutes and 11 o'clock and 11:06 or 11:12, which was spurious. And getting those bits of data out, it can be quite a challenge, because sometimes you're going line by line by line through 100,000 pieces of data.
No, that's not good. I certainly at Ovarro we're thinking about ways that we can do more to help companies to automate these processes and provide tools that will help
it's
do
absolutely
that.
Essential. And to be honest, I think we might have a bit of a change. We're going to probably switch Ronnie and Darren around, as I can see of the presentation that's queued up, because I think we're having a bit of technical challenges getting Sam into the feed at the minute. But yeah, I know Seeq are also going to cover that sort of packaging of data, and so thank you, George. Now, Seeq is a company I came across through LinkedIn, I think about 3 or 4 years ago, and spoke to them. They were over split between here and the States at the time, and I could see all of this data crunching that we're going to have in the following years coming up. I could see it starting to build 3 or 4 years ago. But at the time when I spoke to the person who set up Seeq, Michael Risa, I said, you're probably about 3 or 4 years now. 3 or 4 years down the line, about six months to a year ago, I got asked about, Oliver, do you know any analytic solutions that we can have to handle all this data? And when this when I got asked the question about this flow forum, I immediately contacted Michael over in the States and said, do you fancy having a chat to everybody in the water companies? So at that, I'm going to let Ronnie and Darren take over because I think they've got something really interesting to show us. So Ronnie, Darren, do you take the helm?
Excellent. Yeah, thank you very much, Oliver. Thanks for the introduction, and great to be speaking with you all. Good morning. Still morning. So yeah, excited to be speaking with you all on the subject of data and advanced analytics. So Ronnie Bains, kind of work within the Seeq organisation, responsible for our partnership region. So be a bit of a tag team between myself and Darren Steele during the session today. So I'll hand over to him a few slides. But I really wanted to start with, an introduction to exactly what advanced analytics is and how we position that within the industry. So on that note, can we go to the next slide, please? Thanks. So there are many opportunities, with advanced analytics we see in industry. Data, analytics, all these buzz terms we see within industry really being used quite broadly now across industry, the verticals, but also within the water industry, which is important to us today. Data itself can actually provide us with a lot of values, and it can do a lot of different things depending on how it's going to be used. And within Seeq, we position our platform to really be able to provide three pillars of support to our end user organization. So the first is using that data correctly to enable SMEs, so subject matter experts, to get hold of the right information at the right time, independent of where they may be located. The platform Seeq, which we'll talk a little bit about later on, is really formed on the basis of no code or low code kind of development. So you don't need to be a data scientist to be able to really leverage the value the data that you have can provide. We can easily cleanse and contextualize it, and it's really all about democratizing that data and getting access to everyone. So really enabling those insights to be provided to subject matter experts. The next point is the speed. So the way that we've architected Seeq and how it connects and uses data, both historical data and real-time data, is pretty unique. So it allows us to get those insights developed very quickly. So connecting into existing infrastructure, not providing an overhead to do that, and really integrating into the overall framework that our clients have. And thirdly, we really recognize that democratizing the data, getting access to everyone, is really when the value starts to be seen across industry. So once you have the insights and they've been developed and you've developed correlations and patterns, it's then all about sharing that and within your enterprise and collaborating with other members within your organization and really gaining that value which data can provide us to many of our customers on a day-to-day basis. Okay, next slide, please. Again, when we look at data, and I think probably some of the way that data is treated and discussed in industry at the moment, it's point 4 that you see on the slide at the moment. The computation and the analysis of the data is really where a lot of the focus exists. So how do you gain insights from the data? How do you use that to develop patterns and correlations to help predict things in the future? Which is, of course, a very important point, but really there's a lot more, there's a much larger story to that. And if we step back to point 1, we position Seeq to be able to support the entire life cycle of kind of advanced analytics for the enterprise. So it all starts with getting access to the data, having the right way to connect into your data sources, time series data, being able to bring that in from multiple sources and amalgamate that and cleanse it. Then the next point is being able to contextualize it. So adding real context, real information to that data and how it can be applied. We then move into the ability to be able to search easily, make it intuitive to find your way around that data, index that data, and combine it with all the other sources you may have. And once this has been done, then it's a case of being able to compute and analyze and build correlations up, really extrapolate what that information is telling us, and be able to apply that in the future to really gain additional insights. An important component of this is also developing dashboards, getting the right visualizations in place so the insights you do develop can be shared and collaborated within the organization around whoever that needs to be. So again, the platform allows us to do that. And another important point is, we can start at quite a small point. So we can start at a particular unit level on a piece of equipment, and we can scale very quickly and apply that and grow that as the usage and the value really becomes recognised within the organisation. So it's really all about the entire life cycle, ensuring that engineers have all the information and have the right system, being equipped with the right system, be able to provide them with the support across that entire kind of advanced analytics life cycle that you see on the screen now. Next slide, please. Great. So when we talk to our customers and we really see how data is being put in place to support their digital transformation strategies, they're really focusing on three areas. The first is enhancing the employee's digital skills. So they do that by applying software that's been designed specifically for a task, and it really encourages the collaboration across their teams. This translates into much more or improved productivity, right? Results that really impact operations immediately. And in fact, when we talk to many of our customers, we see payback in weeks, not months or years. It's a really fast return on investment that we can prove, and it's tangible. Secondly, after an initial wave of improvements in productivity, we see our customers really driving towards plant level optimization. So this involves predictive models to avoid costly shutdowns, improved asset utilization, and really increase the production of whatever their facility is doing. And of course, process optimization is put in place there to reduce costs. So it results in millions of dollars or whatever the currency is in the locality of annual savings. So these are the types of returns that we're seeing on a daily basis with our end users we're working with. And finally, the most ambitious type of end users and customers we talk to, they really apply this at an enterprise-wide optimization. So they apply it enterprise-wide and they set up benchmarking activities to really compare utilization, efficiency, cost avoidance, and lots of other KPIs across all of their sites to get a much better insight into how their overall business is performing. So you can do this, and you actually can improve how you allocate capital, where you invest in new equipment and products, so really where to focus on where the growth of the business needs to be. And similarly, again, resulting in a huge return on investment that is tangible and is quick, right? More importantly. Okay, next slide, please. So what you see on the screen at the moment is a high-level topology of the Seeq application suite. So we really have three applications within Seeq, the portfolio, and I'll briefly talk through that just so you get an idea of how it's all kind of fits together. So starting at the bottom, we have different types of data. So it could be cloud data. We have very strong partnerships in place with AWS and Microsoft. It could be manufacturing data, so coming from any of those more kind of recognized manufacturing systems. SQL-based data, custom sources, we're very flexible in terms of what the data source is. If there is a data source available, it's very likely we'll be able to connect to it. Okay. Sorry, a bit of an interruption there. Okay. I'll now hand you over to Darren, who will give us a deeper insight into, and also with his application examples into the water industry, exactly how Seeq can be applied and some of the returns that the customers are seeing in this industry.
Okay, thank you, Ronnie. Hopefully everyone can hear me okay. So my name is Darren Steele, and I have spent most of the last 23 years helping companies to transform their raw data and data sets to deliver decision support systems. More recently, I've been working with Seeq to equip engineers and subject matter experts with what I see as the right analytics software for the job. So as we saw in slide 3 from Ronnie, high quality data is really the foundation for any subsequent analysis. And in this section of the presentation, we'll take a look at different methods that can be applied to the data sets to address a variety of data quality issues. We will then take a look at some real world examples of how analysis can then be made on those cleansed data sets. So next slide, please. There's a small delay between while we wait for the slide there. So okay, so thank you. So if we look at the typical sources of data available for analysis in the diagram on the screen, you will see that we have the traditional sensor-based data coming from sensors up to the DCS or PLC or SCADA system. And we also have, with the advent of the Internet of Things, there's this new data source emerging where you've got sensor-based data that bypasses traditional control system hierarchies. And those smart sensors will wirelessly transmit values with timestamps to a data store that's traditionally cloud-based. And as we heard from the presentation from George Heywood, there are data quality issues with sensor-based data. There's a variety of issues that occur. Issues such as gaps in the data, signal noise, spikes and dropouts, sensor drift, and unexpected staleness in the data as well. However, in order to conduct a well-rounded piece of analysis, we should consider data beyond the sensor data alone. And data is now readily available from third-party providers such as weather service providers and satellite companies that provide observation data. And of course, those data sets are also prone to error as well. Then we have data from relational data sources such as maintenance information, the maintenance work order records from asset management systems like Maximo or SAP PM. And you've got quality data from lab information systems as well. And manual lab sample results, also are prone to error, and also automated inline analyzers require periodic calibration. So with each of these different data sets, you have a potential for data quality issues. And let's not forget, energy pricing spot price information can also be a data source that you can plug in and merge with your operating data as well. And then we also have unstructured data now as well. So there used to be the situation where you'd have the operators would have a logbook and they would record data about the shift, information about the shift in a paper-based logbook. And now there's electronic logs as well where you can record information. That's valuable tacit information about the operation, which we should really feed into and use to add further information to the flow data and your other data sets. The application of that unstructured data and mining that tacit knowledge contained therein is probably worthy of a completely separate session. Now, for engineers that operate and maintain the plant and the network, there's a strong argument for them to be equipped with an analytic system that can be used to cleanse data so that they can deliver maximum confidence in the results of any analysis that they will perform. Next slide, please. So let's take a look at some of the methods and options available to the engineers to clean up their data. So the first use case is around the topic of gaps in data. And this can happen for a variety of reasons, but it will have a significant impact on any calculations and any output from any analysis. So we really need to address this. And there's several options in Seeq that you can use to tackle this. In this example, you'll see there are some blue bars there which are used, which are actually called capsules in Seeq. The capsules are user-defined periods of interest. And in this example, the capsules are used to identify where the gaps in the data occur. And then you have different options available to decide how you want to address those gaps. So in this example, the last known good value is propagated from the start of the gap to the end of the gap. So that's just one option. And that's a very quick, simple sort of no-code example. And there are other methods available. You can splice in an average value if you wish. You can interpolate between the start and the end point of the gap, or you can apply a step function. So there's different no-code and low-code methods available to address those gaps. And those capsules can be used in many ways. For example, if you need to make a multivariate model, we have multiple inputs to generate an output. You really need to exclude bad data. And those capsules can be used to identify periods of bad data or bad quality data and make sure that that isn't fed into those multivariate models. So the capsules can be used in many ways, and also they can be used to provide alerts or flow warnings or operating envelope limit exceptions as well. Next slide, please. So that's addressing gaps in the data. And the next slide will show how we can address things like dropouts and spikes as well. So the engineer or SME, they can see that or apply rules to treat dropouts and spikes. And again, there's several methods available in Seeq to do this. You can create soft sensors where the dropouts have been replaced with derived data values. That's one option. And then that soft sensor can then be used as a more reliable input into the data model or piece of analysis. Likewise, with signal noise, a soft sensor can be made that filters out the signal, the noise around the signal. And there are several filters available in Seeq to do this. So maybe you want to apply a low pass and a high pass filter first to remove those spikes and outliers. And then you can apply an agile filter to remove noise around the signal. So a real world example would be where you're looking to create an alert on a frozen or broken valve, and the noise of the signal may hide the true state of the valve. So it may look like there's movement when actually there isn't any, and you're expecting valve movement. So it's important to highlight here that domain knowledge is often key, really key to selecting the correct filtering method. I'm just picking up some keyboard typing in the background, so I don't know if somebody needs to go on mute there. Thank you. The tacit knowledge and that domain knowledge is really key to applying the correct filtering method here. I think in a ideal world, you could sort of set one algorithm and it would take care of itself. But actually applying the wrong type of filter could actually filter out good data as well. So we have to be aware of that. For example, the Savitsky-Golay method, that's a smoothing filter. That's typically used to smooth out a noisy signal where the frequency span without noise is large. And there are also, it's also called a digital smoothing polynomial filter or least squared smoothing filter. And this filter performs better in some applications than standard averaging filters, because those filters tend to filter out high frequency content along with the noise. That's an example where a little bit of tacit knowledge about what it is you're trying to filter comes in handy. Savitsky-Golay filters in particular are more effective at preserving high frequency signal components, but less successful when it comes to rejecting noise. Let's be careful here when we're deciding what filters to use on which kind of data. Next slide, please. So, in addition to cleansing signals, it should be noted that data streams can contain good quality data, but it could be for periods of bad operation. The data from the periods of bad operation should not be trained into models when attempting to estimate and forecast expected good behavior. I am getting some more noise in the background. I wonder if don't know if anyone else can hear that, but probably just needs some more people to go on mute there. Yes, I still hear that background noise. Okay, right. Okay, we'll carry on. Okay, so The data from periods of bad operation, you don't want to train those into your models. Especially when you're attempting to estimate and forecast what you think is expected good behaviour. If you don't exclude that good data from bad periods of operation, if you don't exclude that, then you'll end up comparing actual versus bad instead of comparing actual versus best. And you'll also be training anomalies into your model. For example, you need to filter out data from periods of unplanned and planned outages. You need to filter out data from periods of unstable operation, and you need to exclude data where you have periods of significant disturbance. You also need different models for different modes of operation as well. So if someone tells you that one asset model fits all, I would be tempted to question that. And again, that's where the tacit knowledge comes in. You really need the engineers and their intimate knowledge of the plant, the engineers and operators with the intimate knowledge of the plant and the network. And that's required to help identify those periods of good operation and then use those, that data to train your models. And Seeq really facilitates this process. And capsules, once again, play an important part where conditional logic is applied to indicate those periods where data should be included or excluded. Next slide, please. Okay. So once your data is cleansed and prepared, you're ready to start analysing your data. And there are a variety of ways to analyse data sets, ranging from traditional descriptive analytics to situational awareness-based analysis. You've also got optimizations, forecasting and predictions, univariate, multivariate predictions. What I also see as well is two distinct types of analysis. You've got that routine analysis, where you build it once and then you want to apply that across your filters or across pumps or across assets, and it's going to be routine analysis. You've also got that ad hoc discovery analysis, and Seeq supports both of those scenarios. Next slide, please. And I think we'll skip on to the next one as well, because we'll look at some real-world use cases of how companies have. Yes, thank you. So here we have some typical use cases across water treatment and wastewater treatment, and we can see a variety of use cases. Ranging from energy reduction to predictive maintenance on equipment and event detection and sort of flow assurance as well. And perhaps one aspect that we should highlight here is the use of Seeq to provide virtual sensors and inferences. The water networks are vast and it's cost prohibitive to instrument the entire network. And instrumentation can also be limited to one or two simple discrete signals on some equipment as well. But Seeq enables engineers to create virtual sort of inferred sensors. That's a more cost-effective means of enhancing decision support. But what we find that anomaly detection doesn't necessarily require fancy multivariate predictions and machine learning. Next slide, please. So in the next example, we'll see how one utility company used their cleansed data sets to help make some improvements. This is Tas Water from Australia, and they recently presented how they worked with a consulting company and Seeq to monitor their pump stations for deviations away from normal profile. Tas Water informed us that sewer blockages were a real issue for them and that they really needed earlier warning of potential blockages to help coordinate more timely remedial action. But this was a challenge since not all pump stations were heavily instrumented. However, with Seeq, they were able to create inferences derived from the pump run cycle times, and then they could create reference profiles. And the earlier warning anomalies were then derived from being able to see persistent and significant deviations outside of those normal profiles. And then they developed a standard usage profile for each pump out station using those reference profiles. Then they could take that single model and use it as a template and then deploy that across other pump stations as well. And now they monitor all pump stations for those large deviations from normal. And it's also integrated with their PI system as well, so they get early warning notifications, and they can send those alerts to the operations center. Next slide, please. So in the next example, this is water treatment sand filters, and this is where they have signals that were susceptible to dropouts, and trying to cleanse all of this data in an office-based spreadsheet and replace those signals, those dropout signals, was really tedious, cumbersome, and it wasted precious time. And not to mention, the challenge of trying to apply that method across all sand filters. A spreadsheet just wasn't viable. And they had a traditional approach of set it and forget it. So they would perform filter washes on a scheduled basis, whether it was needed or not. And the spreadsheets they were using, they were not maintained or updated, so the run lengths were not adjusted, which also led sometimes to solids clogging up in the filter, which meant they had to shut down and replace. And that was time consuming and expensive. So to challenge business as usual, they utilised Seeq, and the engineers were able to create a seasonal predictive model and maximise those run lengths whilst ensuring that the filter washes were performed when necessary. This meant that expensive shutdowns were eliminated and another volatile office spreadsheet was deprecated. By using Seeq to create soft sensors for monitoring metrics such as unit filter run volume and quantifying the cost of each backwash, the engineers could visualize each backwash cycle overlaid on subsequent cycles and also compare to other filters, and then they could check for emerging mechanical issues as well. So in the filter monitoring report, you will then see that capsules appear again as green bars for each cycle, and there are red capsules for the actual backwash events as well. Those capsules appear once again. Next slide, please. So in summary, we've looked at a variety of typical data sources and discussed the need for cleansing data. We also looked at examples of data cleansing operations and the subsequent use of the data for end-user driven analytics. And rather than Seeq being at the heart of the solution, experience really tells me that it's the subject matter expert, the engineers, using their tacit knowledge and the Seeq functions to solve business problems. That's really at the heart of the solution here. And this is a user-driven approach that is really gaining traction across many industries, not just the water industry. So next slide, please. So to end, thank you very much to Ronnie, and thank you very much to the WWEM team for giving us the chance to present today. Be delighted to answer any questions, and also please feel free to contact Ronnie or myself if you'd like to discuss the topics further. So thank you very much.
Thank you, Ronnie, and thank you, Darren. I must admit, I saw Seeq 4 or 5 years ago and went, wow, there's something that we need in the water industry. And I think it's even more and more important now with this mountain of data we've got. To me, certainly the capsules, getting that feed in from the FFT monitor, that feed in from the EDM, and of course all the data quality work has that huge potential for us to overcome. And that's just one application in the water industry. Yes, we're all wastewater flow people on this forum at the minute, but the potential to take that window capsuled approach and bring in the streams, and then, as we saw from Kathy earlier, bringing in rainfall data, potentially bringing in radar data, is such a powerful technique. And we'll see tomorrow actually at the pollution forum somewhere where the hyperlocal forecasting is being used, and I don't think it's used enough. And actually through the Seeq analytics packages here we see here, there's an incredible power that we can take that step on digital transformation from step 1, step 2 that we are now, probably up to steps 4 and 5. I was on a call yesterday with the control room forums, and they were just talking, how do we take that step? And I think they're accepting it's probably going to take 10 years. And in some cases, you can say, well, that power, those tools are here now. So is there any questions from the audience at all? So thank you very much, Ronnie. Thank you very much, Darren. I'm hoping now I've got Sam Greene.
Hopefully you can hear me, if nothing else, Oliver.
I can certainly hear you, Sam, which is great. There's been some work in the background to get Sam on, which to switch the sessions around. So thank you, Sam. I can see you now. It's even better. Great. Sam is going to talk about things from a data quality and wastewater flow compliance perspective. So I'll let you take over, Sam.
Thank you very much, mate. Good afternoon, everyone. As Oliver just said, I'm Sam Greene. I'm one of a few analytics managers at Southern Water, and I've been looking at flow compliance on and off since 2013. And what I'm going to talk about today is actually, from listening to others, going to build on what Kathy said, what George has said, and then what Darren and the other guy, sorry, I've got your name, has been saying this morning. Ronnie, thank you. Sorry about that. So, a little bit about me. As I say, I've worked for Southern Water. I basically am trying to do more advanced analytics inside of the company. We cover every aspect of the company, so we're not flow focused, but we have been doing work on this for a long time. So I'm going to show some examples of what we've done, and I hope tell a bit of a story, I hope. So next slide, please. So why do we talk about flow? What's the challenge? At the moment, flow compliance is quite poorly understood in the industry. We've got quite a few inconsistent approaches of how we can do it. We've got lots of people running on spreadsheets, some far more advanced than others. We have a lot of historical focus that's been elsewhere, which has caused this problem, most of which has been on end-of-pipe compliance. I put in a couple of acronyms here, DRQP, data rich, quality poor, and GIGO, garbage in, garbage out. We definitely have this problem with flow data, with data in general, frankly, but we have this problem with data where we've got a lot of it, but we're not doing much with it because we don't understand the quality. We don't understand what's really going on with it. And we're making poor decisions because we're feeding it with very poor quality information. On top of that, there's a very real operational need to understand what is going on. We need to understand our sites, we need to understand their compliance, and we need to be looking at fixing issues. And again, this is what we've been doing at Southern since 2013, trying to find sites that need to be fixed and then trying to fix them. And all of this comes down to the last point here of compliance and environmental impact. The picture there is actually of the River Ouse, which is right near where I live, because everything we do on flow compliance impacts our environment, our local area, and if we pollute those areas, well, it's not very good, is it? So it all comes back to us. Next slide, please. So, what I'm going to talk about are some data quality pillars. Now, there are lots of models of data quality pillars. I've seen some ranging from 4, and I'd swear I saw one with 13, but I've picked one that has 6 pillars. And those 6 pillars are accuracy, completeness, consistency, timeliness, uniqueness, and validity. Hopefully people know what some of these are, but very briefly. Accuracy, how accurate are the results we're getting? Complete, are we actually getting everything we expect to be getting? Consistency, are we always getting values that are within the range we expect? Are they meeting the sort of values we expect to fit in the database? Timeliness, are we getting them quickly enough or not? Uniqueness, do we have repetition? Do we have issues there? And validity. Yeah, sorry, my brain just went there. Second time I've done this, so excuse me. But for the speech today, what I want to talk about are 3 key areas. And those are accuracy, completeness, and timeliness, as you can see highlighted here. So next slide, please. So, completeness. This one's really easy, thankfully. We know from analog monitors that we are expecting a certain amount of values per day, per week, per year. So these expected ranges, if you're using 15-minute data, we're obviously expecting 96 a day, 35,000 per year. If we get a 2-minute data, 720 per day, 262,000 per year. Trying to look at completeness, am I getting as much data back as I need, is thankfully quite easy here because we know what we're comparing against. But when we go to the next slide, please, you'll see digital monitors. Now this is quite hard to do because we don't know if the if we're expecting this thing to go off or not. We don't have a certain number of expected values per year. So we don't know if this thing's broken. We've got no events. We don't really know what's going on. So this can be quite hard to assess. Next slide, please. So what can we do? Analog-wise, as I say, is actually quite easy. It's very simple to set up, and I'll show you an example of this later on, an automated review of the number of data points that are being returned. You can see quite quickly how many you've got. You can find the gaps very easily, and then you can say to someone, did you know that flow monitor A, B, C, D, E, whatever, that is not returning data as we'd expect. Can you go have a look for me, find out what's wrong with it, and fix it? But for digital monitors, as I said before, it can be quite challenging. So to do this, what we need to start understanding is the site. And this goes from what Ronnie and Darren were saying earlier around actually using SME knowledge. So it's actually trying to understand the site. Do we have regular comms issues? Do we have seasonal patterns of expected behavior? Do we expect the site to actually go to storm or not generally? Have we had long periods where this thing is not activated? And it's actually trying to think about these issues that we could experience, that we can then start designing and building analytical applications or programs that can then review and feedback to people whether we think there's an issue or not. So next slide, please. Thank you. So here is just a very, very quick example of something we do currently at Southern. This is actually used for a couple of purposes, the chart here. It's a frequency distribution histogram. And essentially what we're looking at here is whether the flow control on the site is working or not, and whether we expect the site to be going to storm or not. So what we're using here for completeness is actually for a digital monitor, because we look at the first top site and we say that's got a PFR to dry the flow ratio of 3, or PFF as it's also known, a pass forward rate. So we expect this site to go to storm quite normally. I expect to see activations on my digital monitor. I expect to see a clear flow control peak in my frequency distribution histogram, which is actually what I've got on the top example. Bit hard to see because it's a bit zoomed out, but it is there. The second chart has actually got a PFR to dry the flow ratio of over 6. So for sites like this, where we basically have over-designed back in the day, we do not expect these digital signals to go off. We don't expect to see a flow control peak. We don't expect to see certain issues. So what I'm trying to explain here is, by understanding the site, understanding what we've got going on, and understanding how it was designed all those years ago, we can start looking at our data and saying, do we think there is an issue here with my digital monitor? Do I think there's an issue of it not going off when I expect it to? And one of the things I've actually stolen a quote off here from the EDM Good Practice Guide is it's saying that where we have no events recorded, so we've got a completeness gap in our digital monitors, we should go and have a look. And this is kind of what we're trying to say here on this slide. If you've got a site that you expect to be going off, you can very easily work out if you expect it to be going off or not. If it's not going off and hasn't done for a period, send someone out, get someone to have a look and try and work out if you've got a comms issue, monitor issue, or what. Next slide, please. So, accuracy. So, analog again, this can be relatively easy. I've put relatively for a good reason. But with an analog monitor and a flow monitor, what we're expecting is within a certain band. You don't expect negative flows. You don't expect flows to be exceeding your pass forward rate or your pass forward flow, depending where it's located, of course. And you know the sort of ranges you're expecting based on your connected population and storm estimations. You can know very, very quickly what you expect this thing to be telling you. You also can very easily work out seasonality. You can take the time series, decompose it down, and say, we think we've got flow spikes each winter, as we generally have, and we can actually show this sort of thing. The only challenge is we have a lot of uncontrollable outside variables. And this is where we come back to the weather point that's been mentioned a few times already. You get large storms, very large storms, or very sudden storms, and you can get some very odd flow patterns. But overall, it's quite easy at a very high level to say, is this flow monitor in the range I expect it to, and is it in that range for the right time of year? Next slide, please. Digital monitors, it's still fairly hard. There is an expected pattern to activation. You have a high flow, I expect my digital monitor to go off. Simple. That is something we can definitely build, and we have built. So you say, I've got a flow that's hit PFR, I've not got a digital activation. That's a bit strange. we should go and send someone out to have a look at this. The challenge we get here is there's a lot of potential for interference. And I know Kathy mentioned this on her talk earlier, where she was saying about plant life or wildlife even getting in the way of an EDM monitor and sending it off incorrectly. And it'd be quite hard to work out sometimes if your digital monitor is the one that's broken or your analog monitor is the one that's playing up. It can be quite hard to manage, to work that out. But there's still some things you can do. Next slide, please. So, for this, what can we do is more around understanding your seasonality, trying to build automatic anomaly detections, and I will go on to some things for that in a second. And if you have other flow meters, there are very easy things you can do on site to compare them against each other to say, actually, is this thing operating in the same sort of range as another thing, another flow meter? And we can say, what sort of variance have we got between them? On the digital side, what you can do as well is compare your digital activation to other site assets. Do I have, for instance, say a storm tank level monitor that should be going up when my EDM monitor for the storm tank is saying there's flow going in? If the answer is no, something's gone a bit wrong there. Have I got pumps that aren't running? I've got flow that's backing up, yet I've got no EDM activation. If the answer is yes, there again is something wrong there. There is business logic you can build into analysis to actually look at this. And then the last point here is obviously just checking your site frequently and doing regular maintenance, because obviously if you're not maintaining or calibrating your instruments, you're going to have some problems. But next slide, please. It's just a very busy slide, and I'm sorry for that. But essentially, these are some examples of things we are either doing today or that we're planning to do in the very near future. So I'm going to start in the bottom left, as it is on my screen. That chart in the bottom left with some dots above it. This is a very simple compliance check that we run. This is made up data, by the way. That basically says I've got a flow trend going off. I've got some spill activations going off. Are they happening at or within my expected PFR range? What's going on? But what we can also see is towards the end of the time series, we've got a spike going up. It's hitting the PFR range, but we do not have the corresponding digital activation that we expect. This is something that we do actively pick up. We stick it in a big list and we send it to people saying, did you know that sites ABCD are having this problem? The next one across going clockwise, this is a bit of a messy screenshot, but this is from PyAF, because we also use the Pi system. This is an automatic detector for flatlining and for things going outside of set ranges. And again, we're talking about below zero, that sort of thing. We set this up a long time ago, and it's still run to this day, because we can just have this run 24/7 on a server, always, checking for errors that we think are going on, that when we can notify people via email, because it's got an automatic email system, to say, did you know that this site has had a flatline and it's lasted a day, it's lasted 2 days? You might want to go and have a look at that, because obviously we start falling into technical failure territory if we don't fix these things. And yeah, so that exists. It's a very easy, very quick way of doing things. Just look for values that repeat themselves, tell someone it's happening. On the red and green chart, I'm going to say, on the right, this is a cross-correlation function. So Southern Water installed a lot of monitoring the AMP before last, so we are quite lucky in having a lot of available monitors. What we have done here is we've compared an M-certed monitor at the back end and compared it to a non-M-certed monitor at the front end. What we are doing, and again, this is made up data, but what we are doing is we're comparing the two trends against each other, and we're running them across a cross-correlation function. The idea is that that cross-correlation function will apply an automatic lag, and we'll try and align these two things together, and then we can compare the means. Sorry, there is someone talking. Thank you, whoever muted them. But we can then compare the two means together. The idea is we can then detect drift. We can detect monitors that are inaccurate against each other based on a known validated monitor. So we can say, here's my back-end monitor. It's M-certed. I know it's accurate. Here's my front-end monitor. It's not, but it's actually incredibly close. I know by comparing the means and doing this CCF that this monitor is within the same range, or indeed, as the second chart I've made up, it isn't. So we can start saying to people, did you know this is an inaccurate inlet monitor, this is an inaccurate outlet monitor? We can start actually telling people problems just by comparing the two together. A very simple test, but quite an effective one. And the third thing here is kind of in the middle, and this is something we're exploring at the moment. This is actually taken from a paper. The name of it's actually in that little box. But this is using a sliding window machine learning algorithm. And what that's doing is it's taking a known seasonal trend on water levels in this actual example. from the paper, and it's saying we expect it to be within this sort of range. And it's then saying with a confidence level, is your flow reading within that expected range? The idea is, obviously, we can then use this for 15-minute or 2-minute or 1-minute data. We can dump it through and say, this is my expected pattern, and then try and find those that are falling outside of the confidence interval automatically. So we're still building this, and we're not sure if it's going to work yet. But this paper is based on water level monitoring. It was actually done in China, if memory serves. But we found this paper when we were looking for the new MCERS guidelines, and or the new compliance guidelines, I should say. And we think this sort of technique will allow us to do on scale, very quick, live monitoring of a time series trend with seasonality, and telling us where we have data points that fall outside of what we expect. And again, this is where we start flagging the data points as good, we flag them as bad, or we flag them as ugly or suspect. So we have a lot of work going on here. And again, what we try to do with this is feed it back to the business to let them investigate. There's no point us running this and just sitting on it. What we do every single month is we take all of this, summarize it together in some form or other, and we send it out. Obviously, I say some for other, there's reports, but we send them out regularly to say, did you know these sites have problems? Next slide, please. Timeliness. Okay, I've kind of, excuse the language, bastardized this a little bit. Usually timeliness is making sure people have the data they need when they need it. What I'm trying to say here instead is we need to be considering granularity of data. We need to be considering how small a time period we need to be using to compare to EDM events. So analog monitors, they return data currently, today, every 2 or 15 minutes at Southern at least. And they're giving us a whole range of things. They're giving us averages, instantaneous values, accumulations, and totals. So they're giving us quite a lot of data. But if we move on to the next slide, please. Digital monitors, we have these every second, to the second. So every time they go off, it's a very defined set window to the second of what's going on. And that is either on or off. So we have very rich data sets here. But if you go to the next slide, it's quite hard to compare them against each other. Because then we're saying, I've got a 15-minute flow monitor that's working on averages, which is the best one to use. So we've got 15-minute trend, there's my average, 15-minute trend, there's my average. And then over that, we have a EDM window that says, over these averages, you have had a spill event. And obviously, these things do not always line up. Indeed, we don't expect them to line up. So what I'm trying to say here in the timeless one is we need to focus on granularity. And I believe personally, and it's a bit of a contentious one, I believe we should be exceeding the requirements that we're getting from the agency. When they're saying go to 2-minute, we should be saying, well, actually, I should be looking at 1 minute, because I'm going to get 2-minute EDM reportable windows, and I'm going to have a 2-minute flow, and I'm going to have the same problem. I'm going to have a smaller window to compare against a smaller average being returned. But the more granular data we get, the more confident we can be in saying if we were compliant or not. And if you go to the next slide, please. This little slide here is just trying to very badly show this. So again, completely made up. But you've got an EDM window there. And we started at the 15-minute window where you had very few points. You go to a 2-minute window where you have a lot more, and you go to a 1-minute window where you have absolute tons. And when you compare what we're being asked to do with new guidelines, where it says ignore the first flow or ignore the first 30 minutes of flow, and you think, well, actually, I'm comparing this against a 2-minute window or a 15-minute window, that's going to be really weird to do. It's not going to quite work. So what I believe we need to do is try and exceed these requirements a little bit, and to say, actually, if we have a slightly faster return of our flow data, we could ignore the first point, we could ignore the last point, because we probably should do that too, and we can actually start understanding what sort of flow we actually had during an event. Last slide, please. Or next slide, please, is the last one. So in conclusion, in my opinion, we should be using our data quality pillars and saying, these are the problems we could face. These are the things we should be addressing. By understanding that, we can then build and develop analytics, automatic as far as we can, to try and address and account for all the problems we've got. We need to get business buy-in, because we need to be driving fixes to these problems. There is just no point sitting on something saying this is broken and it's been broken for 6 years. And we need to aim to exceed. And last slide is just questions. Thank you.
So thank you, Sam. 1 minute. 1 minute frequency. Can we actually cope with it?
I think we can. As long as our outstations can cope with it, yes. We have a problem with some of our older kit, obviously, where it might struggle to hold so much information. I personally believe, yes, we can. Modern storage of data is incredibly cheap to store vast amounts of information, and there are a lot of programs, like the one we were talking about earlier, that can actually process reams of information insanely quickly, doing in-memory processing or the like. So I do believe we can do it as long as we aim for automation. If we're talking manual, no.
No, I was going to say, because mostly what we're dealing with now is manual.
Yes.
I would agree with solutions like we've just seen from Seeq, and to be honest, I saw the potential in that a few years ago. That sort of thing, I think we can, yes, put in that data. The outstations won't cope with it, but then again, as we move away from PSTN, maybe there's that opportunity. I mean, for those not aware, the PSTN, which is the old copper phone lines, the private lines on wastewater treatment works are going. Is that an opportunity to then shift over to something that will handle that? I don't know. I don't know the cost of that. And maybe it is, maybe it isn't. I know when I looked at this with a water company, the telemetry bill was gonna absolutely skyrocket going to 2 minute data. So if you're then talking 1 minute, I also know Thames Water of course done the really adventurous thing of universal smart metering, which they're delivering now. One of their problems was data handling the data coming in. Now that they've gone down that route, I've seen their water efficiency manager who absolutely loves smart meters. The insight he's got from the data is incredible. I mean, absolutely incredible. I'd love to go to 1 minute data, but oh my god, it worries me. So we've got a comment from Kathy. Sam, absolutely brilliant presentation. Really reassuring to see Southern's approach to data quality aligns with Thames Water's. You covered briefly how we need to identify sites where we are expecting spills, but hasn't shown, indicating a monitor error. Have you found any useful automated process for this, or is it a manual process at the moment?
Everything we're doing today is automated. So we have written a lot of scripts. So we are code heavy, unlike some of the software you can get off the shelf. We are very code heavy. We have written a lot of scripts in R coding language that process all the data for us with an API giving us easier access to our telemetry data. Essentially, what we've done is we've used our data science team and some of the analysts who work for me to basically build us a lot. And they have built us a lot based on logic we've had back from the business and a lot of learning we've had. As everyone knows, Southern Water's been in the news a lot. We've learned a lot from what's happened. We've taken a lot of these learnings and we've shoved them into code. So everything is automated. We can detect times where we've hit PFR and there's no activations. We can detect times where our storm tank levels aren't going up when we've got an EDM saying there's flows going in. All of this has been automated. We've used R. There are many other options available because ours is insanely code heavy.
So for an organisation who hasn't got you, is it possible?
Yes, and well, yes, there are commercial off the shelf products. I mean, we had one shown to us earlier that can do this sort of thing. I also believe that most companies do have a data team. I found this numerous times working with numerous organisations. Everyone thinks they can do data. Everyone does. And then everyone does it in Excel, or people do it wrong, or they don't understand the principles of what they're doing, and they just end up doing something that could be good. Now, there's good stuff out there, but everyone just kind of thinks they can do data. But companies have data teams for a reason. You have CDOs, chief data officers, for a reason. You have heads of data for a reason. Data is a new industry. Most companies will have a data team. I'd say use their expertise. Give them your SME knowledge. Give them challenges you've got. Tell them what you're trying to achieve. And shove it at them.
as simple as that. Yeah,
it's taken us years. But
yeah, I know, and I'm being facetious there, but it's to me, yeah, I can do things very, yeah. From Kathy, thanks, Sam. Really shows how important data science is to help advance our understanding here. I can do a lot of that. I can look at the data. I can what George presented earlier, and what Ronnie and presented. I can do that manually. I'm one of the subject matter experts. I can look at flow data and go, yeah, there's your problem right there. But converting my brain into automation via a data science team isn't necessarily easy.
No, it's not. Sorry to keep waffling on, but no, it's not easy. There's a framework that I rely on and push to my team all the time. It's called CRISP-DM. It's very standard. It's a cross-industry standard process for data mining. But there are two really key parts there, and it's understand your data and understand what the business is doing with your data or how it's using it. You can't be a good analyst without doing that, and you need an SME knowledge to help. It's not quick, especially on something that requires a lot of knowledge like this. But it's not impossible.
It's interesting because I think really data management wasn't part of Flow or hasn't been part of Flow. I think now if we bring data management, if we bring FFT, DWF, spills the environment, EDM in there, I think really, and I think this is why this particular session this morning was asked for quite strongly by the water companies, was I think data management is now becoming absolutely essential in Flow. And it shows what you're doing and what tools there are out there. And you've obviously developed it for Southern. I think Kathy's doing it in Thames. I think there are companies out there who absolutely need the data skills and don't necessarily have them, which is interesting. So what do you feel with? I mean, I can bring pollution in here really because flow management and pollution almost go hand in hand. We're talking about pollution tomorrow, and the amount of quality data coming up is huge. Where do you see the main pain points? And George, feel free, Ronnie, Dan, feel free to come in here.
I was going to say, was that to me? But no, our pollution analysis is very challenging. Well, we often find it's understanding the root cause. Yeah, the root cause understanding is honestly important. We need to understand what's causing an issue. If we don't have a clear root cause analysis, it's very hard to then predict if it's going to happen again, try and find other sites that could have the same problem, and it's just hard to understand what's going on. So to me, the actual clear understanding of faults is key, and that's something that companies do struggle with because often it's free text. Well, I've seen it in free text a lot, but yeah, that's the challenge in my view.
I was going to say, one of the things I picked up from Ronnie and Daniel saying it was that unstructured data. There's a lot of it around there. I suppose that brings in the situational awareness that we're having. I don't think we've got the situational awareness, or not as much as we've got, and we're bringing in these flow monitors that, with a bit of everything, meld it all together, meld that structured unstructured together, and we've suddenly got a situation we understand much better. So, Daniel, I can't hear you.
Yes. Hi. Yes, Oliver. Yes. I agree. I think there's situations where you're mining the data to detect those anomalies, and then you're sending out engineers to investigate the anomalies, and then it's important to capture the information about that anomaly. So, was it a real anomaly? Or if there was somebody put a plate under the sensor, is that information recorded? And if it is, you can then use that, because then that profile, that anomaly profile, means this is the type of issue that you can expect. And then you can monitor to see, well, if that monitor the data, if that profile reoccurs. And if it does, then you've got a potential apparent cause diagnostic, where you can say, okay, we've seen this error pattern before. The last time we saw it, it was at this site, and and this was the issue. And this is what we recommend to resolve that issue. And this is how long it will take as well to resolve that issue. So you've got all that other sort of follow-on information. I think often anomaly detection kind of throws it over detects the anomaly, then you throw it over the fence, right? Whereas I think, as this evolves, we can add more information around that anomaly to help troubleshoot it and take remedial action.
So it's interesting, because we're getting now, there's this wonderful protocol that was only invented 30 years ago, and a lot of people are talking about the HART protocol. Now we've got it in a lot of the instrumentation, but again, that can help. What you're talking about is almost a multivariate approach at the data level, the sensor and data level. That's, I think, possibly where we can bring in that intelligence, that anomaly detection is from the HART protocol, almost on a separate feed. Now, actually, to be honest, the Seeq platform's ideally set up for that.
Yes, platforms like Seeq, I think, can reduce the burden of code as well. There's some great data science algorithms that you want to tap into and leverage. There's a lot of operations where you perhaps you can't use a spreadsheet to do it. You can't use a business intelligence tool to do it, and your engineers, or you may not have the data science capability to code from scratch. And you don't always want to code everything from scratch as well. So I think applications like Seeq, where it's easy to use, easy to learn, you can actually automate a lot of the data wrangling and take out a lot of the heavy lifting. And then you can plug in, those advanced algorithms from using R or Python, and plug those in into Seeq as well, so that then Seeq allows you to use those algorithms and the data feeds together in one environment, and that might actually be a very cost-effective lean solution.
Yeah, we've also got a nice, interesting sub-chat going on in the chat window as well here, and it's all about, yes, the need for the subject matter expert intelligence, and also adapting probably at a site level. George, I know you've got a lot of experience in that, in looking at the plant level. What are your thoughts on the challenges coming up?
I think that one of the problems here is that we're making a bit of a cottage industry for processing all this data, for manipulating the tools that are needed to analyze it, to validate it, and so on, to review the anomalies that are detected and alerted and so on. I think that the problem here is that we're going to make a lot of work for people to do, and there won't be the people to do it. And I think we need to find ways of increasing automation and making sure that the automation that we're putting in now isn't actually just generating more alerts that more people have to deal with.
Yeah, agreed. It's certainly that skill does worry me, and there's obviously a shortage in data science. There's obviously a shortage in the process engineering, but I look at it, and I quite frequently look at the sums, and when we start shifting to 2-minute data, I start suddenly thinking, well, that's going to be billions upon billions of pieces of data. And you're right, George, it is going to turn into a cottage industry to a certain extent. But in some ways, I'm finding it difficult to avoid that. But I also honestly think with UMON 4 that we're putting in now, we can use that data for treatment works. So we're going to see artificial intelligence solutions tomorrow. And that particular supplier, I've turned around to them and said, well, actually in the future, you're going to get the flow to full treatment monitor, the flow into the works monitor there. How can we use that? And yes, we're doing this on a regulatory basis now, but as we saw from Kathy, there's incredible value from the data. How can we create, and I suppose this is the challenge, how can we create a system where we can manage, we're managing quality through the network pretty well nowadays. How can we create that we're managing flow too? And I think it's going to be very hard to avoid the cottage industry, and I think you're right, George. But have we gone too far down the path? Maybe. Don't know.
Yeah, I think the other thing is that we're all working on the same problems and solving them individually in different companies, and we need to do more to create collaboration across the industry.
Agreed.
to so that that work is being shared. I know that can be tricky, but I think that's what we need.
I certainly think Ofwat would not forgive me if I didn't mention the Ofwat Innovation Fund, and that's probably a route for collaboration. Anyway, I'm not 100% sure if we're live now because I can't see us on the screen. So we have overrun. If we are live and people can still hear me, we've got our third session of the day, which is very much an update on flow technology with Alistair McKinnon from Pulsar talking about sewer network monitoring, and an interesting sensor that I've been seeing developed over the past, well, I've seen it for the past 6 months now, and I know it's been 3 years. So do have a bit of lunch now, and thank you to all of our speakers for this session. I think it's been a really productive session. Thank you, Andrew, for saying you can still hear. So do join us at 1:30, where we will have a bit of an update on the flow technology that's available to the industry. Thank you very much, and see you all at 1:30.
Thanks, Oliver.
Thanks, George.
Thanks, Oliver.
Thanks, Darren.
Thank you, everybody.
Thanks, Ronnie.
Thanks. Take care.
Bye, everyone.
Thanks,
Bye-bye.
Everyone.
Cheers all.
Bye.